So now that we've done a little bit of square roots and we learned how to simplify them, now it's time to dive into how to conduct operations with square roots. So essentially what we're going to be doing in this section is we are going to be doing order of operations like we did in the first unit using like PEMDAS, but we're going to be doing that with square roots. So some of you might be asking, when would anyone even use square roots in everyday life? And to be honest, the answer is really truly endless and spans everywhere in almost every field that math can be used. They're used, for instance, in statistics, finance, electronics, computer science, construction, architecture, physics, and they're also used in very miscellaneous cases. For example, square roots play a role in various situations, such as accident investigations, where they help determine the approximate speed of a vehicle before the driver actually applies or hits the brakes. So the applications of square roots is truly endless in the real world. But before we get into some operations, let's just talk about a couple operation rules. So the first thing is the sum and difference property. So what this is basically if you're adding or subtracting square roots, in essence, you need the term. So in this case, we have x times the square root of y plus w times the square root of y or minus w the square root of y. In essence, what you need is to have the same square root. So for instance, if we had 2 root 2 plus 3 root 2, you could combine these two together and say 2 plus 3 is 5. So you could simplify this to 5 root 2. But let's say instead we would have 2 root 2 plus 3 root 6, for instance. Because this would be 3 root 6, I was saying hypothetically, if this would be 3 root 6, you couldn't combine these square roots because they're two completely different roots, therefore two different values, and they're not like terms. Alrighty. And looking at our second property, we have the product rule, which states that if you have the square root of y times the square root of z, you just take whatever is underneath the square roots and multiply them together into a single radicand or square root. And looking at our final rule, we have the quotient rule, which essentially if you have the square root of a fraction, all you have to do is just take the square root of the numerator and denominator separately, and that's it. So those are the rules. So with those rules in mind, let's simplify the following expressions using the sum and difference or sum/difference property. So as I stated, because we know we need the same square root, I actually encourage you to pause the video and try and solve number 1 on your own. See what you can do. And assuming you've given the first problem a try, let's go through it. So looking at this, we have 3 root 2 minus 2 root 2 plus 7 root 5. Well, because the square root, we have 2 square roots of 2, I'm going to go ahead and combine those. So 3 minus 2 is 1, so we're going to get 1 root 2. And then the 7 root 5 can't be combined with root 2 because they're two different roots. So we're just going to carry that along. And this is your final answer. You could also write your final answer as just the square root of 2 plus 7 root 5 because the square root of 2 is also 1 times the square root of 2, right? They're the same thing. Alrighty, so looking at example 2, we have 10 root 8 plus the square root of 2 minus 5 times the square root of 9. Well, for this example, we actually can do some simplification before we actually go ahead and combine any like terms that we have. Because right now, it looks like we don't have any like terms, but I'll tell you that we actually do have like terms. And this is where the last section, simplifying square roots, becomes very important because the square root of 8, if we recall from the last section, we can create a factor tree. So 8 divided by 2 is 4. And then 4 divided by 2 is 2. We have a group of 2 here. So this first term becomes 10 times 2. And then we're going to carry along what's on the bottom, root 2. And then we're going to add root 2. We're going to carry along the second term here. And then we're going to subtract 5 times the square root of 9. What is the square root of 9? Well, the square root of 9 is a perfect number, right? Because 3 squared is 9, so the square root of 9 evaluates to 3. And now that we've simplified everything, let's rewrite this. So 10 times 2, well, that's 20. So we're going to get 20 times the square root of 2 plus root 2 minus 5 times 3, which is 15. And now we can combine these two terms here, this 20 root 2 and this root 2, because they have the same square root of 2. So we're going to do 20, and then this is like a 1 here. So we're going to do 20 plus 1, which is 21 times the square root of 2 plus, or not plus, minus 15. And that's our final answer. Looking at example 2, we now are going to be dealing with multiplying square roots. So use the product rule of the square roots to simplify the following expressions. And if possible, we're going to fully simplify our square root. Alrighty. So for example 3, we have square root of 6 times the square root of 3. And recall the product rule says that if you have the square root of a times the square root of b, you get the square root of a times b. So in essence, we just take the two integers, 6 and 3, put them under a single square root, and multiply the two numbers together. So we get 6 times 3, which is 18. And I encourage you to pause the video and try to simplify the square root of 18, because the square root of 18 can be simplified. And assuming you have tried to simplify it on your own, let's go through it. Well, I know that since 18 is an even number, I can divide by 2. And 18 divided by 2 is 9. And then I also know that 9 can be divided by 3. So we get 9 divided by 3 is 3. And 3 is a prime number, so we're going to stop our factor tree. Well, I have a group of 3's here, so I'm going to write that in front. And we're left with the 2 here. So I'm going to write 3 root 2 as my final answer. Now looking at example 4, we have the square root of 5 cubed. And I encourage you to pause the video and try this one. And assuming you have given it a go, let's go through it. So we know that something cubed means that we're going to take it and multiply it by itself 3 times. So what this is we get the square root of 5 times the square root of 5 times the square root of 5. Now, the product rule tells us we can just multiply a times b, and in this case, we could do 5 times 5 times 5, which is 125, but 125 would be an awful large number to simplify and create a factor tree for. Now, it is definitely very possible, and 125 isn't that large of a number, but I encourage you to think about it in a different way. So because we have 5 cubed here, we can say, well, 5 times 5, if we were to separate this, we know 5 times, or the square root of 5 times the square root of 5 is the square root of 5 squared, right? And then we're going to carry along that root 5, right? Because this is still the square root of 5 cubed, right? It just looks different, right? Because we know the square root of 5 squared means the square root of 5 times the square root of 5, and we carry along this extra times root 5, and that's still square root of 5 cubed, right? So when we do this, we make our lives significantly easier if we can recognize this, because we know that the opposite of something squared is a square root. So the squared undoes the square root, and we're just left with 5 times the square root of 5. So our final answer is just 5 root 5. Now, if you wanted to, you could use this original rule. You can say 5 times 5 times 5, that's 125. And you could make a factor tree. And when you make that factor tree, you get this simplified answer. Either way is the correct process. Whatever process you'd like to do is correct. Alrighty, so for example 5, I encourage you to pause the video and go through this on your own. Now let's work through it. So we now have 4 square roots going on here. But the thing I encourage you to do is think of it as like you're grouping your like terms. So I have a 16 and a 1 here. I have 2 integers. And then I also have 2 variables. Well, I have t, which we have 1 variable, but they're both t's. So what I'm going to do is think of it like this. 16 times 1 times t cubed times t squared. Like so. And now, well, we have the square root of 16 times 1, which is 16. And we know that when we multiply variables, or when we multiply 2 things that have exponents, we add the exponents. So it's going to be 3 plus 2, which is 5. So we're going to get a square root of 16 times t to the 5th power. And now, all we have to do is simplify the square root. Well, I know that the square root of 16 equals 4. And then this t to the 5th here, well, I know that I can pull apart t to the 5th by saying, well, t times 4, t to the 4th power times t is equal to t to the 5th power because we add our exponents, so 4 plus 1 is 5. And if we put this under the square root, well, we know anything to an even power, it's just the exponent divided by 2. So we know that we can divide 4 by 2, so we get 4t squared, and then we have this single t on its own, and that's your final answer. Alrighty, so looking at example 3, we're now going to use the quotient rule, which at essence, we just simply take the square root of the numerator and denominator and simplify. So for example 6, we have the square root of 256 divided by 49. While using that quotient rule, I know I'm going to have the square root of 256 divided by the square root of 49. Well, the square root of 256 is a perfect number, 16. And the square root of 49 is also a perfect square, which evaluates to 7. And that's it. That's your final answer. Looking at example 7, we have 12 times the square root of 12 times z cubed, all divided by 18 times z squared. Well, I'm just going to simply rewrite that as 12 times z cubed over the square root of 18 times z squared. And now, these don't evaluate to perfect numbers. So what we're gonna have to do is create a factor tree for the square root in the numerator and denominator. So we have 12 and z cubed. Now I can write z cubed as z squared times z. And then 18 in the denominator, we have 18 times z squared. And I'm not gonna change anything about this exponent because it's even already. So with that in mind, let's create some factor trees. So 12, I know I can divide by 2. 6, I can divide by 2. Oops. 6 divided by 2 is 3. While here, I can pull apart a square of 2. And then here for our variables, we have z squared, which that is a perfect square, so we're going to have a z out in front. And then this z is left on its own, and so is this 3. So we're going to get 2z times the square root of 3z. And then we're going to divide that by the square root of 18 times z squared. Well, I can say 18 divided by 2 is 9. 9 divided by 3 is 3. We have a pair of 3's here. This 2 is left over. And then we also have this z squared here, which we know evaluates to z. We still have that 2 though, so I'm going to write root 2. And now that we have that, let's see if we can simplify anything further. We'll notice that there is a z here in the numerator and a z here in the denominator. And since this variable z is being multiplied to everything, and the same thing for the denominator, these variables cancel. So we get 2 times the square root of 3z, all divided by 3 times the square root of 2. And that's your final answer. Looking at example 4, now we're just going to solve a couple word problems that require the use of square roots. So for example 8, we have the floor of a square room is covered with 81 square foot tiles. And we want to know how long is each side of the room. So this requires a little bit of geometry. So we know that the room is a square. And we're given that the area is 81 square feet. Well, recall from geometry, right, the area of a square is just base times height. So we're going to have two unknown variables, x and x, our base and our height. And we know that when we multiply those two together, we get 81 feet squared. Well, looking at this, right, if we set 81 feet squared equal to x times x, base times height, and we want to solve for x, right, what we can do is, well, we know that x times x equals x squared, and I'm actually going to remove this unit here, feet squared, for now. So we just get 81 equals x times x, right? So what this translates to is 81 equals x squared. And we want to know the length of just one x, right? We want to know the length of each side of the room. So one side of the room. So to figure that out, well, we know that to solve for x, we need it on its own. And since x is squared, it's not fully solved for. So what we can do is square root both sides. So we get x equals the square root of 81, which is 9. And that's your answer. And looking at example 9, we're given a rock is dropped from a bridge that is 81 meters above a river. Now, ignoring air resistance, we want to know how long does it take for the rock to hit the water. So, given the distance d, an object falls in time t is given by this equation. So we know that t represents time and d represents our distance. And we're also given this variable g, which represents gravity. And we're also told that gravity is a constant, which is 9.8 meters per second squared. So let's plug in what numbers we're given. So we want to know how long does it take for the rock to hit the water, which we want to know how long, so we want to know the time. So we're given that t equals the square root of 2 times d, where d is distance, and we're given the distance here, 28 meters. So we know that this bridge is 28 meters above the water. And we're going to divide that by gravity, which is 9.8. Now let's simplify this. Well, we know that using our quotient rule for square roots, we're going to take the square root of the numerator and denominator individually. And we can also figure out that 2 times 28 is 56. So now, when you evaluate this in your calculator, you're going to get approximately 2.39 seconds.